Waves are quite interesting as they have many different properties including amplitude, wavelength, frequency, period, and speed. Some of these are self-explanatory, such as speed, which is the distance that a wave travels in a certain amount of time, and wavelength, the length of the wave from one crest to the next. Amplitude, frequency, and period require additional explanation, where amplitude is the height of the wave and it affects how much energy a wave has. Waves can have amplitudes from the nanometers to meters. Frequency can be defined as the number of times that the wave passes through a point in a second. This term is measured in reciprocal seconds or hertz. Period is simply the reciprocal of frequency and can also be defined as the time in seconds that it takes for a complete wave or one wavelength to pass through a given point. Additionally, each wave can be expressed in terms of c, the speed of light, where c equals lambda times nu. Lambda is the wavelength and nu is frequency. The two variables nu and lambda are inversely proportional, and it can be applied where a wave that has a smaller wavelength will have a greater frequency because more waves pass the same point in the same amount of time than a longer wave. As one progresses through the EM spectrum, these properties vary with each wave. Starting from the weaker end of the spectrum are radio waves, very large electromagnetic waves that can span up to several kilometers with relatively low frequency. These waves are good for transporting information across long distances because they don't significantly affect objects that they travel through due both to their size and frequency, so they don't carry a lot of energy. Moving down the spectrum, we have microwaves, significantly smaller waves with wavelengths ranging from a meter to a millimeter, with much higher frequencies. The wavelength and amplitude of microwaves are much smaller than those of radio waves, and these properties combine with frequencies from 300 megahertz to 300 gigahertz, giving them a wide range of applications such as heating water in a microwave, as well as applications such as radio frequency engineering. Following microwaves, IR waves or infrared waves have wavelengths down to the micrometers, from 700 micrometers to 1 millimeter, right at the edge of the visible light spectrum. These waves, while invisible to the naked eye, can be detected as heat by people. They are divided into three categories based on their wavelengths: near, mid, and far infrared, and each had different applications. For example, near infrared is used in heat lamps. The visible light spectrum is the most well-known, and a small range of wavelengths includes everything that the human eye can see, from violet to red. It ranges down to around 300 to 400 nanometers, and there are many obvious applications of optical visible light, primarily including allowing people to see. However, others include spectra, the idea that different elements absorb certain wavelengths or colors of light. Ultraviolet waves are on the more powerful end of the EM spectrum, getting their name from the color that they're right next to, violet. These waves include UVA, UVB, and UVC, and are all produced by the sun. These waves range from 400 nanometers to 10 nanometers and are much smaller and higher frequency than the preceding waves on the EM spectrum. Following UV rays, X-rays are far smaller, typically reaching the size of an atom. They are much higher energy with much shorter wavelengths from 0.03 to 3 nanometers. X-rays are typically divided into soft and hard X-rays, with hard X-rays having much more energy, which allows them to also be used in a wide range of medical and industrial applications. The most powerful end of the EM spectrum includes gamma rays, with wavelengths smaller than the nucleus of an atom. Since both X-rays and gamma rays are too small to measure, they are more commonly measured in electron volts, which is based on the energy of the wave. High energy waves such as these are able to pass through objects simply because they have so much kinetic energy, especially on the higher frequency end of the spectrum.
With that said, gamma rays are typically produced through the radioactive decay of atomic nuclei. When a radioactive nucleus decays, typically through the emission of an alpha or beta particle, the resulting nucleus is usually left in an excited state, which is then calmed down or decayed to a lower energy state by the emission of a gamma ray photon called gamma decay. Radioactive decay of isotopes, such as cobalt-16, an isotope with relatively weaker decay, can be harnessed by people to use in various medical and industrial applications. The reason for this is that gamma rays have properties similar to X-rays, where they have lots of penetrating power and are able to essentially be aimed to only affect a specific spot if guided properly. Without this, gamma rays can easily pass through objects and even people without having any effect.
Danger is often the first word that comes to mind when gamma rays are mentioned, but the intense, energy-packed rays also have a surprising application: industrial radiography. Industrial radiography is a non-invasive inspection method that utilizes high-energy gamma rays and X-rays to inspect materials, structures, and machinery. Often used on infrastructure, such as pipes and roads, industrial radiography checks for cracks and other structural defects that could shorten the lifespan of an object. Without it, cracks and pipes and pores in concrete would go unnoticed, putting infrastructure and lives in danger. There are two forms of industrial radiography, X-ray and gamma ray. In both forms, X-rays or gamma rays are directed from a source into a tube. This tube concentrates the rays and guides them to an area of inspection. The rays then pass through the object, colliding with the structure and any defects. The remaining rays are absorbed by a film on the other side of the object, producing an internal image. In the image, a majority of the object will appear dark, as most of the energy was absorbed into the object. However, cracks and other defects will not absorb as much energy, as the defects produce gaps that let the waves freely pass through, giving them a high contrast appearance on the film. As their name suggests, X-ray and gamma ray radiography refers to the type of wave that's used. In X-ray radiography, high-energy, hard X-rays are used, while in gamma ray radiography, gamma rays are used. To produce X-rays, a small synchrotron is used. Synchrotrons are mini-particle accelerators that accelerate electrons in a circular path. Anytime a particle is accelerated, energy is released in the form of light. Because the electron is accelerated to near light speed, it gives off a much higher energy form, X-rays. Gamma rays, on the other hand, are beams of photons, massless particles that carry energy. These photons are sourced from the nucleus of decaying atoms and carry the energy that is emitted from this decay. In industrial radiography, the source of this decay usually comes from cobalt, iridium, or selenium. The main mystery behind industrial radiography, or any wave imaging in general, is how the particles pass through objects. Taking a closer look at the energy each wave carries answers that question. The penetration ability for any wave is dependent on the energy it carries. If a wave contains enough kinetic energy, it has the ability to pass through an object. When a wave passes through an object, most of its energy is absorbed, stopping the wave. If the energy is high enough, however, then the object has enough leftover energy to pass through the object. Hard X-rays and gamma rays contain the most energy of all the waves on the EM spectrum, ranging from 10 kiloelectron volts to above 100 kiloelectron volts, explaining why they can pass through virtually any object.
Hi, Post-Production Surge here. As a man of industry myself, the EM spectrum and industrial radiography are two pretty important things. So, if you want to find out where we got all of our information from, learn more about the EM spectrum while you're at it, check out these sources right over here. Now, I'm gonna get back to playing with some household electricity. Ah! 石のように硬いそんな石で塵も積もれば山となでしこ死ぬ気でいや死ぬ気で